In this lecture, we are going to continue image formation. In particular, we are going to look at how the image is formed on the resist. Right. So, we know how the intensity patterns are created on the wafer. We saw that in detail in the last lecture. In this lecture, we are going to look at how that variation in intensity is transferred onto the photoresist. So, the image contrast on the photoresist is what brings out the solubility change that we are expecting to create in this photoresist, right. So, an ideal image should have a step like function, because this is, let us say this is a grating, right, and you want to reproduce that grating image, and your ideal image should be also of similar nature. So, you have a high intensity and a low intensity, right, on the wafer. But it is in real image you will not be able to reproduce a perfect square image, but you will have something of an oscillating or a cosine type image as we see in this real image, right. So, the metric that we use to quantify whether this image contrast that we have is sufficient to create the modulation that we are looking for on the wafer or on the photoresist is called modulation transfer function. So, the modulation transfer function is nothing but the ratio of maximum to minimum intensity that we have, right. So, the I max is the maximum intensity and I minimum is the minimum intensities you have. So, this is our I max and this is I min, right. So, you want the ratio to be large enough, right, so that you can transfer the image reliably. So, for a 50-50 fill factor, so what do we mean by 50-50? This is nothing but the duty cycle, right. The line spaces are equally done. So, if I take a pitch of 100 nanometer, so if my pitch is 100, then my line is 50 nanometer and my space is 50 nanometer, right. So, this is 50-50 fill factor, right, in those kind of structures. So, the I min, if I min is 0, what that means is this is 0, right. So, if this is 0, then we know the pitch that we are using is below the limit, right. So, the below the limit of this system, right, so that you are able to reproduce the image clearly. But if my I min is I max, right, so that means there is no contrast at all, right. So, there is no contrast. So, there is no contrast at all in this system, and that means the pitch that I am using, right, is greater than what the system can offer, right. It is beyond the resolution. So, the modulation transfer function in that case is 0, right. But a perfect reproduction where your I min is 0 will give me MTF of 1, right. You can just plug in the MTF equation and you will notice that you can swing between 0 and 1, right. 0 is where you have very poor or no reproduction at all of the image, and when it is 1 you have perfect reproduction of the image, right. So, anywhere in between this we will have a partial reproduction, and that is reasonably good for a lot of application. We will see that in the next slide why you do not need 1, right, in order to reproduce this image. And this image contrast, of course, is a step like function, as I said, right. So, if it is 1 you create the image, if it is 0 you do not create the image. So, we have to make sure that we create this contrast, right, by tuning and adjusting our energy and also the focus, right. So, let us look at how this image is formed on the resist, right. Now, let us take an ideal situation, right. The image is perfect, right. We have a perfect square like pattern, And the resist contrast is also perfect, right? We have a step-like function, right? Just to recap, your contrast is going to look something like this, right? So you have energy versus remaining thickness, right? So we saw the contrast curve to be something like this. So what we are assuming here is a perfect contrast curve. That means it's a step-like function. So if we take a perfect image and a perfect resist contrast, then the image that you will get on the wafer is also a reproduction of that intensity that you had, right? It's again a perfectly reproduced square like pattern. Okay, so in an ideal condition, perfect imaging is possible, right, when you have high contrast image and high contrast photoresist. And now let's look at more practical, right? And this is again not the practical situation, but in a partial, right? So the image here is not perfect square. So here we see the image contrast is not 1 anymore, right? It's less than 1, but again it's not 0, so it's in between 0 and 1, right? But then the resist contrast is perfect. I have a perfect step-like response. So when I image such a profile with a resist that has perfect contrast, then I can reproduce a perfect square pattern on the wafer. So this is the resist pattern, right? I can reproduce that. The reason for that is the resist contrast, right, actually takes care of the variation here, because there is only one threshold point, right? So power's optical intensity beyond this will dissolve will not dissolve my photoresist, and power below this will dissolve, right? So this is again an example of using a high contrast or perfect resist with a non-ideal image, right? This is again for understanding purpose. Again, this is not really practical because it is impossible to get a step-like resist contrast. You will always have some slope, and that is what the final practical real image case, right? So here we have non-1, right, less than 1 MTF modulation transfer function. And now the interesting thing is the resist contrast has a slope here, right? This is more practical approach, right? So when you take something like this, when there is a projection of these different intensities, then our development is also going to be, or your resist is also going to follow the same profile. So it's a combination of resist slope and my intensity slope here. So now you are unable to form a perfect square-like pattern. You will form it with some slope, and this is more practical. So if you take any resist image, this is what you will see. And one can increase the dose, right? So one can increase the amount of energy that we put in order to remove the remaining photoresist and try to reduce the slope to some extent by increasing your intensity or exposure dose. But the bottom line is, in a real image you will have a sidewall, right, that is a reproduction of your photoresist contrast. But then again you should be able to solve this problem by using your development process and baking process that we saw earlier, right? So the resist process technology will also be useful in addressing this slope issue. You can make this reasonably vertical. Okay, so this is how we transfer the pattern from the contrast, image contrast that we have, or intensity pattern that we have, onto the photoresist pattern. So now we understand how the image, the change in the intensity profile is converted to a three-dimensional pattern on the photoresist. But let's look at some important practical scenarios. Right? So the interference is the main process that you want in order to create image, right? But then so far we did not discuss anything about the wafer flatness, right? Here we assume that wafer is really flat, right? So there is no warping or there is no non-uniformity in the wafer thickness. But that assumption is ideal. But in real world you will always have some flatness deviation. So you will not have really flat wafers. So if that is the case, you want to have some defocus limit, right? Your optimal focus is somewhere, but if there is any change in the thickness of the wafer or any flatness variation in the wafer, you want to make sure you still can reproduce the same image, right? So how do we understand that? So that is understood by depth of focus, right? What is the depth of focus? So I would like to bring one of the practical scenarios that you must have encountered this when you are using optical camera, right? In this case, a manual camera. So if you want to focus onto an image, so what you will do is you will change the lens position, right? So you will be in focus, and if you go beyond that optimal focus, the image will get blurred. And then also under focus will also make the image blurred, right? So the concept here is exactly the same, right? The optimal focus that we all talk about is that perfect image plane, right, where everything is in focus. But then if that image plane is not flat, if there is any change in the flatness of that image plane, you are going to go into the defocus regime, right? And defocus, we all know, will not reproduce the image quality that we are looking for, right? But even when you are in optimal focus, if you change the focus very slightly, right, some of you can try this. If you change very slightly, you will not see any change in the quality of the image, right? Both plus or minus, right? So there is a delta, right? There is a tolerance that you can give to this focal plane within which your image quality is maintained. Only beyond this, your image quality is going to degrade. So this is what we call depth of focus. And this depth of focus in our case depends on the interference that we have. So let's look at how this depth of focus is determined, right? So let's take this wafer which is flat, and then if there is a change in the focal plane, right, because of wafer bending or the placement of the wafer and so on, we need to have some defocusing depth, right, within which you should have perfect imaging, and that's what we call a defocus width. And this defocusing width, not only the flatness of the wafer but also from the diffracted image orders as well, right? So this is the 0th order, and let's say this is +1, right? When you take a lens system, the 0th order directly goes through, but the first order does this, right? So you are going to capture it through some means. And now your assumption here is both of these diffraction orders are in phase, but it is not true, right? Because the first order, the 0th order, travels straight, and the other one takes a certain distance, right? And also the lens is not really flat, so you have the lens profile. So the path length, the optical path length could be different between these two orders. So that is the optical path length difference, and this optical path length difference will also create change in the phase, right, when they come and interfere onto the surface. So one need to also understand this path difference will also bring you defocus, not just because of wafer flatness. If you have flat wafer, you could still have some path difference, right, and that will also create a defocus of the image on the wafer, right. So let's understand this defocus, right. So what is this optical path difference, right? Let's try to find how this is related to the optics, right. So here, if delta is the defocus that you have, right, delta minus delta cos alpha. So the cos alpha is the angle between the first order and the 0th order, right, and this is what will give you the optical path length difference. And if you use the identity and if you deduce it, this is nothing but delta times alpha square over 2. So this is what you are going to get as path length difference. So you can replace alpha, right, for small alphas, you can replace it with Na. We all know sin alpha is your Na from our earlier discussion, and your optical path length difference is related to, you know, your Na, right. So earlier we saw having larger lens will allow us to collect more diffraction orders, right, and that is useful because the more orders you collect, the better your image is going to be. But if you look at optical path length difference, right, optical path difference, your Na is in numerator. So if you increase, and it is square as well, right, so if you increase your Na, your optical path difference is also going to increase, and as a consequence of optical path length difference, you will have defocus effects, right. So you will not be able to image perfectly on the image plane, you will have defocus problem. So one need to be very careful about choosing your Na. Don't choose very large NAs. So this will create imaging problem, and this is what another reason when you are doing microscopy, you want to restrict to a sweet Na. You don't want Na to be very large. So you always try to make Na large to capture more light. So when you increase Na, you are also reducing your focus depth. So your focus depth becomes very, very thin. So you have to have very precise movement in order to get that imaging done. So your Na is a deciding factor here, right. And let's look at what happens to the imaging when your OPD, right. So optical path length difference changes, right. Let's put a number to this OPD, right. So if OPD is equal to the wavelength that I use, right. So the path length difference that I have is order of the wavelength, right. So if it's the same as the wavelength that you have, in that case you will not find any phase difference at all, right. So this is again coming back to our interference discussion, right. So you have a wave, and then the next wave is lambda. So this is lambda, right. So this is as a function of distance, and this is your wavelength, right. So now we say OPD is one wavelength, right. So this is point A and point B, let's say. So now point A has moved to point B, right. That means you have one wavelength movement, right. So now point A is here and point B is here. In this case it has moved one wavelength, but if you look at the phase is exactly same. There is no change in the phase. So no phase difference. So you will not see any difference at all in the imaging, right. So there is no problem whatsoever if your optical path length is lambda, right. So you cancel out so that you will not have any phase difference. But now if the optical path length difference is lambda by 2, right. So this is where you run into a problem. So if your OPD is lambda over 2, then it is pi phase difference, right. And the phase reversal between these two orders will create an opposite phase image, right. So there will be an inverted image what you will get, okay. So one need to be careful when your phase difference is lambda over 2. So what that means is if you have lines in your mask like this, right, and then when you illuminate it on your wafer, this is on the mask, right, and on your wafer you will have complete image reversal. So wherever you wanted line you will have a trench, and wherever you wanted a trench you will have a line, right. So there is a total image reversal you will see in this, which is undesirable, right. And let's look at the other case, right. The other case is when your OPD is lambda over 4, right. So in that case your phase difference is going to be plus minus pi over 2, right. So the pi by 2 is going to be your phase difference that you are going to get, and this actually is an interesting scenario where you will get a frequency doubling, right. So what I mean by frequency doubling is you have a pitch of P, let's say, right, and then when you image this, you will get frequency doubling, that will be 2P. So you can increase your or rather decrease your pitch, right, by using this kind of patterning, right. So the frequency actually doubles. So in that case this should be let me correct this, right, and this should be something like this. So is it desirable? Definitely not, because you actually wanted pitch P, right, but you are getting a smaller pitch, right. And another question is whether my next layer is prepared to accept this sort of variation, but definitely not, right, because whatever you have on the mask is what you want on the wafer, right. So that one should be clear about, but it might look really fascinating. Okay, in my mask I only have P, but I can double my pitch. Is it something interesting? You certainly will be tempted to do that, but the problem here is when you do this frequency doubling, your image contrast, right, your MTF that you have will go down, it will be very poor, right. The aerial image you will see double pitch, right, but then your MTF will be very poor, so you won't be able to reliably reproduce, right, actually remove all the resist that should be exposed and to create that image, right. So it is not advisable to tune to these phase differences. Okay, so just to conclude, your depth of focus, right, is a factor of Na, right, and your wavelength. So if you increase your Na, your depth of focus is going to reduce. So one should be careful when choosing Na, right. We should not be ambitious to increase your Na, but that will result in very poor depth of focus and image quality. So so far we discussed about this depth of focus. So depth of focus is a practical scenario, right, which will happen all the time, and one need to measure and assess the condition. And the other important thing is about the illumination itself, right. So far we only take the light source that we have as coherent. So what is coherent? That means all the photons coming out are in phase. That means one single line laser, right, very narrow line. But lasers do have a line width, right. It can be few tens of picometers or hundreds of picometers, depends on the quality of the laser that you use. Here at least it will have few picometer line widths, right. So and this line width means the photons are not all in phase. So the light is not in phase, or in this case highly coherent. There will be partially coherent, right. So that is a practical scenario, that's a reality. Let's see how the imaging is going to be affected if this partially coherent light source are used, but in practice that is what we use. Okay. So let's look at the incident first of all, right. So here all the incidence is with a perpendicular incidence, right. So there is a pi by 2, all of it, right. But then in reality your light source will have some angle, right. So there is a shape to the light source, right. So you will have some variation in the angle at which the photons are coming out. So there will be a slight angle, right, that these guys come out, and that will have a direct influence on the diffraction orders that we get, right. So where this order is imaged. So let's focus to this mask and look at what is the implication of this angle, right. If you remember in the normal incidence, we had a situation like this, right. So we had a situation like this, right. So where we said, and this is your delta, right? So the additional distance the wave should travel before interfering. But in this case, we have two path length difference because both of them are at a slightly different angle, right? So there is an incident angle and there is a exit angle, right? So there are two angles and there are two different optical paths, right? Two additional optical paths that one need to consider, and the condition for constructive interference now is delta H that we have and the delta L, right? And that should be in the order of wavelength, right? So n lambda. We saw if it is n lambda, then you preserve the phase sanity, right? So then we look at the exit and incident, right? And now your diffraction pattern looks slightly different, right? It's not, initially we had sine alpha equals n lambda over p, right? So this is what we had when we had normal incidence. So now we have slightly oblique incidence, and this oblique incidence brought us this additional term, right? And now let's progress and see how this additional term is changing our diffraction order pattern, right? So now you have two orders here. It's not anymore 0. There is a crowding around 0, right? And the distance between this is nothing but sine beta over lambda, right? While the axis is sine alpha over lambda, right? Again, the other things are definitely constant, but we are just looking at what is the extent of this splitting of this different orders because of this oblique incidence. So this is something putting together both normal and oblique incidence. You can see here the diffraction from the normal incidence and with slightly different angle. So I'm only taking two distinct cases, but in reality there will be a continuous variation between this and this, right? So there will be multiple rays going to come in, and in that case it's not anymore two distinct order, it's going to be also continuous. So if that is the case, then instead of taking just an individual beta, we take beta max, right? So that is going to be our the incident angle term, and the incident angle beta on the mask, this depends on the optics that we use, right? We try to reduce this beta, right? We don't want too much oblique, and that is the reason why your condenser or the illumination optics becomes very important, where we control the angle of incidence of this incident light onto the mask that we have, okay? So this is how it looks like, right? It's a continuous variation, right? So now we don't have a single diffraction order, we have a band now, okay? So we have a 0 band, +1 band and -1 band, right? So this becomes very interesting. So we don't have any single order, you have a bunch of orders crowded around this, right? And the width of this is given by sine beta max over lambda, right? Twice that, right? Because it's a symmetric between plus and minuses, right? So this is the width of this band, and one can calculate this by understanding NA, coherence and wavelength, right? So let's look at what is the definition of partial coherence, right? So what do we mean by partial coherence? Partial coherence is nothing but a ratio of the size of your source and your lens here, right? So the radius, the RA is nothing but this, and your RS is nothing but this, right? Your RS and this is RNA, right? So if this is your RNA and your R source is this, right? So this is nothing but the radius of R, the source, and to NA. So your numerical aperture radius is definitely much larger, and you will have diffraction as I mentioned, right? So beyond the size of this, and you can also have beyond this, right? You will have beyond this, and your NA is going to restrict those diffracted orders, right? So it will not propagate beyond the NA plane, in this case the lens plane that we are talking about. And by using this size, we should be able to find the coherence, the partial coherence. And we can also understand by looking at the numerical aperture. So there is numerical aperture of the source and there is numerical aperture of your pupil system or the projection system. By using this physical quantities, we should be able to measure the partial coherence. And now let's look at how this partial coherence is helping us. So the other way to do that is by looking at the incident and also projection angle, right. So one can also look at from the optic side, but this can be also measured other ways as well. So now this is my NA plane, right. So this is my NA, my pupil lens, and these are all the diffraction orders, right, coming from my mask, and this is the image of it, right. So this is my 0th order. I can call this as -1, +1, and this is +2, and this is -2, and I'm capturing 0th order, first and second order, right. So this is how it looks like. But now let's look at the resolution limit if I use this partially coherent, right. We know that we at least need 2 orders, right, 0th order and first order. So we know from our earlier discussion your resolution is dictated by lambda over NA, right. So now it's not anymore NA, right, it's sigma over NA, right, is what is profiling your resolution, right. So now the theoretical limit is not just lambda over NA, it's lambda over NA 1 plus sigma, right. So this is what gives you your additional factor when you use partially coherent, right. So now if you look at this equation, right, sigma is in the denominator, right. When you are in the denominator, you are going to pull this pitch down, right. So if you get a non-zero partial coherence, if it is 0, it is coherent. So sigma is non-zero, right. So if it is non-zero, you are going to increase your denominator. So that means you can make finer feature, right. So you can increase your resolution, right. So now by using partially coherent light, we can increase the resolution. So it is not a disadvantage, right. It's not is going to affect our system if we go from perfectly coherent light that we theoretically looked at to a partially coherent light, which is practical, right. So how do we understand this, right? Let's try to understand. Mathematically this is all correct, but let's practically understand how this resolution increase can be brought in, right. So in this case I would like to look at this image, right, where you have 0th order and then you have -1 and then you have +1. So in this case definitely the orders are, when I take coherent light, these red marks are coherent, right. So now if this is my NA that I am going to use, definitely my +1 and -1 are outside my pupil plane, right, outside this lens that I have, right. So I won't be able to image this the structure that I have, right. But now I have a partially coherent light, and that means I have a band around this, right. So in this case I have little bit of these diffracted orders coming through my lens system, right. So I have not changed anything, right. I have not changed the pitch. I am only looking at ideal coherent case and then partially coherent. In a partially coherent system, there is a very small overlap, and this small overlap will get my +1 or -1 into the system. So this partial overlap is good enough to get my 0th order, right, that I have here, and my -1 order, right. And with these two I will be able to image the feature that I had, right. If I used a coherent light, it is impossible to image. They are far away from my lens plane, right. So this is how we achieve higher resolution by using a partially coherent light in the place of a coherent system, right. So So as a summary, the practical systems that use a partially coherent light, right, as a coherent source, highly or with a single line source, it's impossible to achieve. But in practice, we always have a partially coherent source, and that partially coherent source is actually helping us to improve our resolution as opposed to ideal coherent light source, right. So just to summarize, in addition to this optics, we saw depth of focus, right, which is again a very important parameter, how one should be careful about choosing the numerical aperture and how many orders that we have and so on. So we don't need too many orders that will influence our depth of focus and our imaging quality. So overall, we need to be careful about the numerical aperture that we have and the coherence of the light source in order to create better imaging on the wafer.